Navigating the stratosphere using a high-altitude balloon is difficult due to the horizontal motion being fully determined by the wind field. This complexity poses challenges for long-term environmental surveillance, atmospheric analysis, and communication relay. Current research into stratospheric balloon navigation investigates the use of superpressure balloons. This can inhibit high-altitude research due to the cost and lack of adequate altitude control equipment. In comparison, latex balloons are more accessible and can be assembled by non-specialists. In this context, our research investigates the use of reinforcement learning to control latex balloons, operated by venting helium and ballasting sand. We evaluate our approach for the task of station keeping, where the objective is to maximize the time spent within the target radius. Previous work has investigated using discrete-based reinforcement learning for superpressure balloons. Superpressure balloons use high-strength plastic which halts the expansion of the lifting gas. Once inflated, the density is fixed and the buoyant equilibrium is achieved. Air can then be pumped in and out to alter altitude. In comparison, latex balloons use a highly elastic polymer which expands during ascent, maintaining a very small pressure difference. Due to the low overpressure, the buoyant lift force of the latex balloons remains roughly constant with altitude. As a result, we require a finer grained control scheme than previous methods. More specifically, venting and ballasting accommodate for larger ascent rates not possible for superpressure balloons. Hence, we propose the use of soft actor critic to utilize larger ascent rates to reach more favorable wind speeds in less time, while optimizing the use of resources to extend the duration of flight. We use the ECM-WF ERA5 wind forecast to generate data and linearly interpolate at the balloon's location. Researchers have investigated the accuracy of the wind forecasts and found there exist biases of less than roughly 0.5 meters per second and standard deviations of 3 meters per second. To solve this, previous methods augment the wind field with simplex noise to emulate forecasting errors and generate plausible wind speeds. The vertical motion of the balloon is derived from the buoyancy, weight, and drag forces. To obtain the displaced air and air density, we model both helium and air as ideal gases. The state space consists of a combination of the local wind forecast and onboard measurements such as position and bearing to the target. Taking inspiration from previous work, we sample wind vectors from equally spaced points between the vertical pressure limits at the balloon's current position. The action space is a representation of the desired ascent rate, decomposed into 3 actions: desired altitude, time factor, and float. By modeling the balloon in steady state, we can then calculate the helium to vent or sand to ballast. We bound the desired calculated resources to incorporate physical limits and prevent the environmental exploitation by the agent. We reward the agent based on distance away from the target, either giving it +1 or the exponential distance from the target. We train a soft actor critic using a Gaussian stochastic policy and 2 double soft Q networks, all parameterized using a feed-forward network with 2 hidden layers of 256. The soft Q network parameters are trained by minimizing the soft Bellman residual, and the policy parameters are trained by directly minimizing the expected KL divergence. The entropy regularized framework maximizes the trade-off between the expected return and the entropy of the policy, which is tuned during training. This exploration strategy can prevent the agent from getting stuck in a local optimum, especially where we want the agent to use larger ascent rates during the later stages of training. On the other hand, we want to ensure the agent doesn't overuse balloon resources to explore, which could be caused by alternative random exploration strategies like epsilon greedy. We compare our method against the current state of the art, which uses quantile regression DQN to control a superpressure balloon. Using the metric of average time within 50 km radius, the results showed our method achieved an equivalent score of roughly 25%, illustrating latex balloons can achieve equivalent navigation performance while being more accessible. We notice a significant variance in both methods' performance, which can be accounted for by the wind field characteristics. A certain proportion of the wind fields contain uniformly orientated winds or exceptionally high wind speeds. Diverse wind directions are required for station keeping, and high wind speeds can cause the balloon to deviate quickly from the intended path. Furthermore, the agent learns quickly how to conserve resources. After 25 episodes, the agent no longer runs out of resources and can fly for the entire 3 days. For our future work, we intend to implement our method on a physical balloon. Thank you for listening.